Alex Popham, the 4-H agent in Breckinridge County, part of UK's College of Ag, Food and Environment's Cooperative Extension Service. And today we are continuing our exploration of 4-H science, engineering, and technology programs, and we'll be dissecting a starfish. And here's a big shout out to our Breckinridge County Middle School scientists as well as our 4-H biotechnology teams in Cloverport. I hope you enjoy this lab. And you can follow along with our starfish dissection lab manual as you complete this virtual dissection. So we'll start off today looking at our specimen up close. We do have a sea star, or more commonly called a starfish, but it's actually not a fish, it's an echinoderm, just like a sand dollar. And unlike humans that have bilateral symmetry, a starfish has radial symmetry, so it's radiating out and you can divide it in a lot of different directions and it's still symmetrical. And the benefit of that radial symmetry is that there's a repetition of organs in each of these rays. So if a starfish loses one of its arms or rays, it can still survive and these other organs will pick up those functions. So it's pretty cool. You'll see starfish with missing arms and they're still kicking it, still alive, and living it up in the salt water of our marine systems. So that's the type of symmetry. We're also going to be looking at the external features. So I'll start out here with our central disc, this central region on the aboral surface. And one of the cool features on the central disc is this madreporite, this lighter colored and hard structure that is actually connected to the water vascular system within the starfish. And we'll talk more about that when we get into the actual dissection. In addition to the central disc, there are rays. This particular species has 5 rays, or 5 arms, and that's just species specific. Some starfish usually have 5, some 10, some 20, or even more than that. All right, I'm gonna flip it over, point out all these spines. So there's lots of spines on the top surface for protection from predators, as well as on the bottom surface. But you'll notice here in the center is the mouth, and it's surrounded by lots of oral spines, and there's spines all on the underside. Not only is that for grasping prey as it's feeding, but it also helps it hold on to surfaces and provides a little extra protection. Now, in addition to the mouth and all these oral spines, if you follow out on the rays, there's an ambulacral groove running down the middle here. And if you poke the inside of that groove, you'll see all these tiny squishy little tube feet. That is another structure that's part of that water vascular system, and we're going to get to check that out a little closer soon. And these little tube feet, they will expand and shrink due to their water vascular system and hydraulics, and that will allow this starfish to grasp onto its prey. It helps the starfish actually walk or glide. They appear to glide thanks to these tube fish, and it also helps them hold on to surfaces. So very important, lots of multitasking going on with these tiny little squishy tube feet. I'm gonna flip the starfish back over onto the aboral side so that we can get started with our dissection. And to do that, I'm going to take my sharp scissors and I'm just going to cut the end of one of these rays off. And I've now created a hole that I can get my scissors into. And I'm just gonna cut along the sides through that endoskeleton, so you can probably hear it crunching as I cut, going all the way up the ray, and I want to do the same on the other side, so I'm basically creating a flap. And you want to keep it as shallow as you can, cutting up. And then once you have cut the ray, you'll continue cutting through the central disc. You're gonna cut around, but when you get to the madreporite, you do not want to cut through the madreporite. So you're gonna kind of swoop and miss it, kind of angle it out, and then come back around so that you end up with one complete flap. And for the sake of time, I've already cut through the central disc and around that madreporite on my second sample over here. So we'll switch trays. And I have a tray here with a different starfish, same species, but a little larger. And I've gone ahead and cut up through the rays, across the central disc, making sure not to damage our madreporite right there. So I cut kind of inward and missed that madreporite. So what I'm gonna do is peel up, doing my best not to remove the internal structures. Now, these digestive glands here tend to stick to the top of that endoskeleton or that top flap, but these are all just digestive glands that create those enzymes and things that are attached to the stomach here and help digest food. So I'm gonna set that to the side for now. If we look in the central disc where the stomach is, I'm gonna pull the stomach out, and I've gone ahead and cut it away from the central disc using an X-Acto knife. But this stomach is made up of two chambers. One of the chambers will remain in the central disc and the other will exit the body. It's usually a thicker, more muscular part or chamber of the stomach. And it will exit the body and surround its prey and start digesting its food outside or externally from that starfish. So it's pretty cool when you see them feeding. They'll shoot out through their mouth, that one chamber of the stomach, and start digesting their prey. And that would have been connected to these digestive glands here. Once you remove the stomach, you're going to have a great view of the water vascular system. So if you think back to that madreporite, it's going to allow salt water to enter in. So the water is going to enter in the madreporite. It's going to go down this stone canal right here and into this ring canal, and out into these lateral or radial canals that are attached. They have all these little ampullae that are attached to the tube feet that we looked at earlier in that groove. So water will come again into the madreporite, down the stone canal, around this ring canal, and out into the lateral or radial canals. And the water will enter those tube feet. Muscles will contract right here, and the water will squeeze into the tube feet, and that allows the tube feet to move. Again, those tube feet are important because they help the starfish walk. They help it grasp its prey and hold on to any surfaces that they may be laying on. Now, the water vascular system also helps the starfish excrete waste. And then one final thing I want to make sure and point out in this particular ray is you'll see these gonads that were underneath all those digestive organs, all those digestive glands. And those glands or gonads are where the eggs or the sperm would be produced. Starfish are male or female, but they're hard to tell until they exert or squeeze out those eggs or sperm into the water. And the egg and sperm will meet, and the eggs will be fertilized externally in the water, and the starfish will not have any kind of parental care or guidance over their youth. So they develop, on their own without their parents. So it's pretty cool. I love dissecting starfish because you can do this singularly and just dissect one ray, or you continue and check out that repetition of all those digestive glands and gonads and all the cool water vascular system that we saw that function very similar to the hydraulics of, let's say, a tractor or other pieces of machinery. We get lots of inspiration from nature, just as you see from this starfish or sea star. So that concludes our sea star dissection. I hope you enjoy it. Make sure and complete your lab manual, and have a great day, guys.